Hi, hello, welcome to the lesson on algebraic vectors. So in the previous lesson you did geometric vectors and you added them using the picture format. In this particular unit we are going to move and write them as equations so that you can use your algebra skills. So the goal, you can represent and draw vectors algebraically, and then you can perform operations, and I'm referring to your standard algebraic operations of adding and subtracting in order to find a magnitude of a resultant. So, if we want to use vectors algebraically, we got to go back and we got to discuss grade 10 trigonometry. It all comes back from knowing how to do grade 10 trigonometry. And I'm talking about something called components. And basically what we're doing is we are taking our right angle triangle and we're breaking it into what I call components. So this is what we call the y component, so the vertical component, and here is the x component. So with vectors, if we use or assume the hypotenuse is our resultant vector, alright, so it's going to be our resultant vector. The angle of interest then will be down here at the tail of the resultant. So I can take any vector, and it doesn't actually have to be the resultant, so you can leave the resultant there, but let's call it any vector. I'm going to name it a u, but you can leave the r there. So if I want to determine the x and y components for this vector, so that means that what I want to do is, instead of going from point A here directly to point B, I want to follow a road map where I stay on the x-axis for a while and then I go on the y-axis. So I just want to break it into just an x, y value. So how do we do that? Well, we simply use SOHCAHTOA. So it's going back to what you did in both grade 10 is where you first learned it, grade 11 it was reinforced, and now it's why this is the whole purpose of doing the trigonometry. So it's the end of the road for you here. So using SOHCAHTOA, we know that if this is our reference angle here, angle theta, then this side is our opposite, or our O. This then is our adjacent side, and this would represent our hypotenuse. So there we are. So if I want to start with the x component, so I want to simplify the x component. We know the x component would be cos, so cos of the angle, that's a over h. So our angle then, cos theta, would equal, so our x component, and I'm going to leave it as a for the moment, and our hypotenuse, well, that is the length of our original vector. So if I rewrite this, we know that the base, or the x component, is the magnitude of the original vector multiplied by cos of the angle. Alright, and that's our x component. Alright, so again, we're trying to create a road map getting us from point A, except instead of going directly to B, we're going to take along the x-axis. So that value there that I just got will calculate how far along the x-axis you need to travel. Similarly, the y component then would be using the sine law, or sine ratio, so it's opposite over hypotenuse. So sine theta equals, opposite is what we're interested in, so I'll leave it as O. Hypotenuse again is how big is that vector, so we end up with the opposite equaling the magnitude of u sine theta. Okay, and that's our y component. So that tells me how far up the how far up the y-axis I have to travel. So if you're asked then to rewrite the vector as an algebraic vector, we could take the vector u, which is the one that was in red, and I can break it into its x, y components, and it would look like this. The magnitude of u cos theta I plus magnitude of u sine theta j. So those u's, okay, that is the size of original vector. Alright. And these new I and j are what we call unit vectors. And they tell us which way it's pointing. So for example, the I is always to indicate x-axis, and j is used to indicate y-axis. X-axis and j represents the y-axis. Okay, so this is the formula that must be on that cheat sheet that you're creating. All right, in order to solve. Now, the nice thing with this, I'll finish it off in the bottom here. If I have this algebraic equation, how do you find the angle theta? So down here, let's look at it from the reverse. If you have a vector, so I'm just going to draw a line here. So what happens if I tell you that the vector v is equal to 4i plus 3j? What does that mean? That means that if I am looking at a vector, if I go 4 units down the x-axis, and then I go up 3 units up the y, there is the vector v that I was talking about. If I want to find that angle theta, again from SOHCAHTOA, I know that I have my opposite value and my adjacent value, so I can find that angle. So that means angle theta comes from using the tan trig ratio. So tan theta would equal your y component over the x component. So it ends up being theta equals the tan inverse of y component over x component. And there's a formula then. The second formula that you want to make sure is on your cheat sheet. So these two go hand in hand together. All right? So how do you use this stuff? Well, let's take a look. We've got a couple of examples. So this is very similar if you look back to yesterday's homework. If I have vector u, which is 10 units long, vector v, which is 5, and the angle between the two vectors when they're placed tail to tail is 30 degrees, I want to find the resultant. So this is the exact same example that you just finished there the other day. So what's it look like? So I'm going to put the u vector right there. The v vector looks something like that. So I know that the u vector is 10 units. I know the v vector is 5 units. I know the angle between the two vectors is theta. Oh, which is 30 degrees. I actually know that. I don't have to put theta in. It's 30 degrees. And Smartboard's not playing nice. There we go. 30 degrees. All right, so u and v. So what do we need to do? We need to convert these to algebraic, because instead of using the triangle process you used yesterday, I want to use the algebraic method. So where does this begin? It looks like this. It's like adding, it's like elimination from grade 10. We have our u vector. I'm going to add it to my v vector, so I'm going to a stacked notation. And when I add those two vectors together, I end up with my resultant vector. So what does the u vector equal? Well, remember the formula I said you need to have. U vector equals magnitude of u cos theta I plus magnitude of u sine theta j. That's so important to have either memorized or on a cheat sheet or formula sheet, because that's what you're going to be using the next couple of days here. So I'll shrink that, keep that to the side. So this is what it's going to look like. The u vector is 10, and because it's already pointing horizontal, I can just say it's 10 units down the x-axis plus no j, because it doesn't go up or down, it stays horizontal. So it's 10 units to the right and 0 j, so there's no j component or no y component. The v vector, I have to use that angle. So you take the magnitude of the vector, 5, cos the angle, cos 30 I, plus, because I would have to go up. So if I was following it, I'd go to the right, and then I would go up, which is a positive, so plus 5 sine 30j. What this allows me to do, it allows me to add my x components up here, and it allows me to add up my y components to end up with the resulting xy components of the final vector. So you're just going to use the calculator to add the columns. So 10 plus 5 times cos 30 equals 14.3 I. And if I want to find The other one, it's 0 plus 5 times 30 sine 30, which would be 2.5j. All right. So there is the magnitude of our resultant, the magnitude of the resultant. Now, how do you find the information about it? How long is the resultant and how's the angle? I showed you on the previous slide how to find the angle. And it's tan inverse of y component over x component. So tan inverse of 2.5 over 14.3. So that's going to give me an angle. So 2.5 divided by 14.3 tan inverse gives me an angle of 9.9 degrees or 10 degrees. Now how do I find the magnitude of this vector? Well, remember, if I go back to the original grid here, and I imagine that there is an xy axis, what will the resultant look like? Well, I'm going to go 14.3 units, so that means I'm going to go past 10 units. I'm going to have to go over here into my question a little bit. So there's 14.3, let's say. And then I'm going to go up 2.5 units. So that means that the resultant vector is right here. If I were to add those two vectors together, that's where the resultant is. So the angle is the angle at the origin, so how far I had to rotate. How do I find the magnitude of the resultant? Well, you notice that it forms a right angle triangle. So we're just going to use Pythagorean theorem. A squared plus b squared equals c squared. All right, and I'll shorten it up for you. The magnitude of the resultant is always equal to square root of your x component squared plus your y component squared. So that's the nice thing with the algebraic process. The algebraic process is very repetitive. It's a recipe. It works the same way every time. So if I use the formula then, magnitude of my resultant will equal the square root of 14.3 squared plus 2.5 squared. Calculating that out, so 14.3 squared plus 2.5 squared square root. I get 14.5 units. So my therefore statement, vector r is magnitude 14.5 units, and the direction is to the east or to the right. Doesn't matter which one you choose. I know it goes right because my x component was positive, and I also know my y component was positive, so that means it's going to head north or up, and the angle I just calculated was 9.9 degrees. So there we go. There is the example with some explanation in there. So please make sure this also gets added to the formula sheet. And I've got, I think, 2 more examples I wanted to finish up, and I'll do that in the next video.